So I'm super excited to be here. And what I'm going to be talking about today is the work that we've been doing, myself, my PhD students and I, about how to revisit concurrency control in database systems. So very, very briefly, hopefully this is all something I'm preaching to the choir here. You know, database systems are, I'm going to argue, the most important thing in the world, or almost. And they're still the most important thing today, even as people tell us that AI is going to replace database systems. And the reason for why I think they're so fundamental and they're essential to continue working on is because they provide this nice abstraction, consistent way of querying structured data that is easy, that provides ground truth, and that's what's going to enable you to build the high-powered AI applications that introduce the uncertainty. So they provide the ground truth. And because of that, they're increasingly being asked to support, more concurrency, more transactions, and they're being placed under pressure. Higher write throughput, they're being placed under pressure and tortured for fun and profit. So, like Julian said this morning, and like Mike Stonebreaker said, one of the best features of database systems is that they provide transactions. They provide these very nice abstractions that no matter how many operations you do, if you wrap them into a transaction, they'll take effect atomically. If you start a transaction, if you read and then you write, and then you commit, then either all the operations will take place or none will. So that makes it very, very easy to program, and this is why even things like Data Lake today and Cassandra, while they went away with transactions initially, have started adding them back. And so we're seeing transactional systems becoming increasingly transactional and supporting higher degrees of correctness. So the gold standard that we all want, we don't always achieve, but we want is serializability. We want this nice abstraction that no matter how many concurrent operations you'll have, the execution will remain equivalent to a serial schedule. If you have this two transactions here where transaction 2, the read transaction reads the write of transaction 1, then it should always be possible to reorder the schedule such that transaction 1 takes place fully before transaction 2. Nothing very new here. The part that's interesting and we're going to focus on here is the mechanism by which we achieve that, and that's called concurrency control. So concurrency control is the mechanism through which you ensure that no matter how and in what order transactions arrive and conduct operations, the end result will look either serializable, snapshot isolation, read committed. It'll enforce the correctness guarantee that you want that the database has spec'd out. And the way that it does that is by mediating conflicts between concurrent operations that access the same data. And the key challenge is obviously that you want to do that as quickly as possible. Because if I tell you that I'm going to mediate conflict by, having a nice cup of tea, taking a while to think about it, and then returning, you're not going to be very happy. So there's been a large amount of research on improving concurrency control. And the key thing that people work on, so the public enemy number one when it comes to designing concurrency control is data contention. So it's a fundamental aspect of many databases, many workloads that run on databases, which is that you're going to have hotspots. Lady Gaga is going to post something at some point, and everyone is going to want to read or write to that post. There's going to be young engineers who maybe design their new application inefficiently. Or there's just going to be long-running transactions in the background that do some kind of garbage collection or cleaning. All of this fundamentally introduce contention. And while you can design around it in many cases, from talking to many of customers that use pretty much all database vendors, they all agree that it is a fundamental part of many of their workloads. So the consequences of data contention is that you're going to get low throughput, so the number of transactions per second is going to drop precipitously as transactions contend on the same data. And also, you're going to struggle to get performance isolation between multiple clients. Because if I am executing a 10-minute long transaction on an object that you are waiting for, then suddenly your application is going to suffer. So concurrency control is designed to handle this contention. And there's been a lot of different research on concurrency control. There's a lot of approaches. You can be pessimistic by acquiring locks, that's two-phase locking, which we've all seen in the past, and many database systems like MySQL operate under two-phase locking. Optimistic concurrency control, so that's where you assume that conflicts don't happen, and then you abort at the end if you were unlucky and a data conflict did occur. And then more sort of optimized ones, like the core of Microsoft Hackathon, so based on timestamp ordering, where you can be a little bit smarter and you assume there's an existing serialization order, and you try and align with that serialization order. And it's still an active research in the academic community. Every year, there's more and more, there's new concurrency controls are being developed. I did this search yesterday, and if I search for 2021, and I try to sort of ensure I'm getting relevant results, there's about 2,000 results. So obviously this is overestimating, but every year at the sort of top database conferences, there's new concurrency control research happening. And I'll sort of split it into three categories. The first one is research on smarter ways to detect conflicts. So what is a true conflict or what is not? Can I do complex static analysis dependencies such that it looks like a conflict, but actually it is not a conflict? Or maybe I can do cycle checking so that I only abort when there's a real danger, so on and so forth. So smarter ways to detect what a conflict means. Because fundamentally, optimistic concurrency control and locking are very coarse-grain hammers to detect conflict. They're correct, but they don't try and distinguish between what looks like a real conflict or what, if it smells like a conflict, it's a conflict. The next is cheaper ways to detect conflict. So how can we design more efficient concurrency control mechanisms that fundamentally do the same thing? Now, this was especially relevant in memory databases, for example, where just getting a counter turned out to be a bottleneck. And most database systems actually heavily rely on the existence of a counter, at least a timestamp. And so much work was done in how you can actually design what looks like a counter cheaply for a multi-core system. And finally, concurrency control that are tailored towards specific deployments. So, for example, geo-replication. You cannot write the same algorithm if you are going to be running locally, distributed, or across different geographical deployments. Unfortunately, the industrial impact, and I have many of those papers, so I'm also going to be shooting myself here, to be clear. The industrial impact of concurrency control research has been fairly limited. There are success stories, so the current Postgres concurrency control system is based on a long line of research that started from quite theoretical to this paper, serializable snapshot isolation in Postgres. Now, I'll highlight the unusual authorship of the second author, the Wisconsin Supreme Court. But Dan Ports is a researcher who took the long-lasting line of research on serializable snapshot isolation, namely a cheap way to achieve serializability by bolting on a few additional checks on top of snapshot isolation, and actually implemented in Postgres. And to this day, it's still the default Postgres checker. And more recently, there was another piece of work that modified the MySQL lock scheduler to better handle tail latency under extremely high contention. But otherwise, it's not, you don't see a huge amount of tech transfer from the academic world on concurrency control specifically into industry. And I'll wager that it's because most conversations that you try to have with looks kind of like this. So this is me, I'm teaching with my little teaching stick, and the database engineer, so the practitioner is to the right with the HTML code. Is contention a problem with your customers? Usually when we talk to people, the answer is yes. Not all workloads, but most people will see hotspots at some point. So far, so good, it's promising. Concurrency control is sometimes a bottleneck for developers. I can make your concurrency control faster by 10x. Beating Postgres by 10x or MySQL is almost a rite of passage for a database PhD student. Not always 10x, sometimes it's 2x, but you kind of expect those numbers in conferences. So that should be easy, right? I can get you 10x performance improvement. And then that's where the trouble starts. Will it require much code changes to my well-tested system? How many test engineers do you have to actually have checked that this really sensitive piece of code that stores the ground truth of my data is correct? And then the answer is, well, about 1,000 lines, so a pretty good chunk of your system. And I tested it, my PhD students tested it, and then usually people hang up. So I would wager that one of the key challenges of doing research on concurrency control systems is that they're so foundational to the correctness of the system is that no one wants to change it. You know, if it's not broken and people aren't yet complaining about the performance, or they're only sort of grumping about it, they're not actively complaining, then people aren't going to change it. So that puts us in a bind, because we know it's an important feature. We know this performance we can still get, as evidenced by the fact that most PhD students will beat MySQL by a factor of 2, just by changing the concurrency control. But we can't do it without investing a significant amount of time upfront and almost joining the company and doing the changes. And even then, it's not easy. So what can you do instead? Well, we're going to make conflicts disappear instead. Now, usually when I say this, people look at me and say, did I really wake up at this early and come to the East Bay for this? Like, it's a little bit akin to saying, if you don't want to get wet when it rains, just don't make it rain. So obviously, I'm advocating for a pipe dream. But slightly more specifically, what I mean by making conflicts disappear is that if we can engineer the workload in some way such that conflicts become rare, then it doesn't matter how slow your concurrency control is. Then the concurrency controls that we have today become infinitely faster, because if there's no conflict, if there's no contention, then a slow concurrency control, or at least a simple one, will suffice. So let's look at what I mean by this. So what concurrency control protocols fundamentally do is that they take in requests from a request queue. So here we have, number of transactions. The different colors represent different transactions, and the commit is just the commit of the transaction. And they take these and execute them. So taking a simple view of the database where each time unit is, each operation takes a time unit, you'll execute an operation. If you take the next operation from the queue, if it doesn't conflict, you can execute it concurrently, assuming you have the threads to do so. So here, operations are accessing Y and X, they don't conflict. The next operation follows, is also from the blue transaction, so you just execute it in the next time step. And then the red operation here does conflict with the blue operation, but the blue operation has finished. So you can just run it in time 2. And it's taken you 2 time units to do it. So effectively, a concurrency control protocol takes transactions in a request queue and forms an implicit transaction schedule. So once it's finished executing, you have a partial order of transactions that reflect the order in which it will look like in the serial schedule. And it took execution 2 to do it. Now this is all pretty basic, and I know you all know this. The reason I'm emphasizing is because I want you to start thinking about the role of concurrency control, which is just to find a schedule, to find a transaction schedule based on the request queue that you get. That's the fundamental sort of role of it. Sometimes you get lucky. So in the first case, it was a pretty fast schedule. If transactions, however, had arrived in a different order, so let's say that the red transaction, operations from the red transaction had arrived first, followed by the blue one, then the schedule that you get from this, because databases all process transactions in FIFO order as they arrive, would have looked somewhat less nice. So you'd have executed X first, followed by Y, and then because the first operation of the blue transaction conflict, it couldn't start before the red one, and so now the schedule would have taken 4 time units to execute. So just by chance, just based on the order in which transactions were in the request queue, we've doubled the time it takes to execute a transaction. And that's the crux of the issue. Most concurrency controls take transactions in FIFO order from the request queue and are reactive in that they say, ooh, there's a conflict, let me handle it. So they deal with conflicts after they arrive. They handle it well and they can be as efficient as they want, but they just treat the conflict as something that exists and something that you cannot change. what we want to do in this line of research that we're starting and that we've been doing is that we want to be proactive. Specifically, because some conflicts are harder than others to handle, we're going to try and plan for those conflicts and ensure that these hard conflicts that lead to slower schedules do not happen. So again, rather than executing transactions in the FIFO order that they want and dealing with conflicts after they've materialized, at which point there's not much you can do, or if you have to be extremely smart and that's a costly implementation, we're going to try and schedule transactions intelligently and proactively minimize the impact of conflicts. And that brings us to transaction scheduling. So transaction scheduling is a simple question, which is, given a set of transactions, find the schedule that minimizes the execution time. That is going to be done by finding the schedule that maximizes concurrency, so the number of transactions that can execute concurrently, and by minimizing the cost of individual conflicts, by which I mean if you acquire a lock and you have a transaction, you have a number of transactions waiting for you to acquire that lock, that's going to be costly. So minimizing the impact of the conflict on others. Those are the two things that you need to do to find a cheap schedule. And once you find that schedule, you can just enforce it using your favorite concurrency control protocol, which means that you don't have to change the database systems, and you're not touching that correctness that others have worked extremely hard to ensure, and which I, as a researcher, can only dream to achieve. Now, the small wrinkle about that is that scheduling transactions based on conflicts, well, that requires knowledge of the full read and write set. Already, we're off to a bad start, because most transactions do not give you full knowledge of the read and write set. Some do. I think Meta's graph framework has all the read and write set up front, but most transactions, and certainly SQL, doesn't expect that. The second issue is that, people proved in the 1970s that transaction scheduling is NP hard, meaning that even for n transactions, you have factorial number of schedules. So very, very quickly, you get to your scheduling problem taking you, time to make coffee, boil pasta, you name it, but you're not going to schedule transactions fast. So these are the two issues that we have to handle. The first one is knowledge of the read and write set, and the second is the fact that transaction scheduling is fundamentally an extremely costly problem, and that's why people haven't done this in the past. But we're optimists. I wish say it was sunny outside, but it's not. But normally in California, it's sunny outside. We like the sun, we're optimists, we know we can do it. We know we can fix this. So let's see how. So the first problem, knowing the read and write set. Well, it turns out that we're not very inventive in how we write transactions, fundamentally speaking. Most transactions come from programs. They're templates. They're web apps with 5 to maybe 100 different transactions that are written in code that you instantiate with different requests. And those requests are often specified at the start of the those input data is often specified at the start of the transaction. So while you don't necessarily know the full read and write set, you actually know quite a lot about the transaction itself. The second observation is that simple, greedy algorithms for scheduling transactions perform surprisingly well. We're able to show that for the sort of standard database TPC benchmark, we actually come close with a simple, greedy algorithm to finding optimal schedule, not all the time, certainly, but most of the time. And that drastically, obviously, will reduce cost. This was a surprise to us, but it performs really well, and I'll explain why in a sec. So these are two things that we're going to look at to try and make that approach tractable. So like I said, most transactions are fairly well defined. Applications contain some amount of transactions, 5 to 100. They either access it through code. This is a snippet of a standard database benchmark. I think this is auction marks or the auction system, and you kind of write it through the JDBC driver, replace JDBC by whatever you prefer, or you're using it through an ORM. This continues to be true today, even as we're going to see agents generate more transactions. They're still going to follow a particular pattern, and the space of transactions that you generate is not going to be completely random. They're going to be recurrent, potentially with different inputs. They're going to have similar patterns, or we can enforce them to have similar patterns. So using that, we've been able to demonstrate that you can predict the read and write set with fairly high accuracy if you only know the initial input to the transaction. And using that, you can use a very simple sort of classifier based on this input and based on some small amount of training data to predict the read and write set. So you know the initial input, and then with pretty high accuracy, you can end up predicting the rest of the keys that the transaction is going to access. Now, the important thing that I want to say here is it's okay to get it wrong. We're not trying to do this for correctness. We're trying to do this for performance. And so we don't need to be right all of the time. If you give us very little information, if you only give us one input parameter out of 100, yeah, maybe we'll get it wrong, at which point you're not going to see benefit. But for most workloads we looked at, it's with some amount of training data, fairly small amount, we can predict with fairly high accuracy. So the way that we can do it is by leveraging two types of hints: transaction types and hotkey inputs. So transaction types is, if you think of a benchmark, there's maybe 7 transactions: new order, delivery, payment, so on and so forth. This is the template that you're instantiating. So you can either learn the template using statistics inside of the database, or you can specify it as an argument to the database. Both work. The second is the hotkey inputs. So most of concurrency control the performance of concurrency control is driven entirely by how you handle hotkeys. And those hotkeys tend to be specified as the input to the transaction, or very early on in the transaction, because people tend to write them early to minimize the impact of contention. So using those hints, we can map those types of transactions to fairly simple metadata vectors, summarize the hotkeys and the positions in the transaction, find the optimal number of clusters, aka the different transaction types that you're going to run, cluster those based on the Euclidean distance, and end up with basically 7 to 8 different transaction types that have a canonical set of hotkeys mapped to them. So basically we're saying, hey, your workload, well, in reality, you have maybe 10 clusters that all access these hotkeys. So when a new transaction comes in, we can just say, use that classifier to predict what hotkeys it's going to access based on which cluster's in full. It's not perfect, but it works quite well. So that's the first step. How do you actually predict the read and write set? So again, we use a classifier to optimistically get the canonical set of hotkeys, and then when a new transaction arrives, we can very cheaply check which hotkeys that transaction is likely to access. The next is the greedy algorithm. So how can we actually find fast schedules? We know the read and write set now, well, let's assume that we know it with reasonably good accuracy. How can we actually find those fast schedules? So the intuition is, again, almost surprisingly simple, which is that we're just going to schedule the transaction that increases the execution time the least. So let's say that I have scheduled 5 transactions already. I'm just going to look for the transaction that makes my schedule the least bad. That's fairly intuitive. That's common to a lot of scheduling policies. Schedule the X that makes the execution time the least bad. What this is going to do is effectively create pockets of concurrency, where if I'm executing transaction A, then if transaction B and C don't increase my execution time, it means they're basically concurrent. They basically don't conflict, or those conflicts are cheap to handle. And so by searching for those transactions that increase execution time the least, we're going to create these pockets of concurrency, which are going to guide us towards finding those really efficient schedules. That's why we call our algorithm shortest make span first, where make span here means execution time. So we're going to start the schedule with a random transaction. Turns out it really doesn't matter which transaction you choose from in the request queue. And then out of all transactions in the queue of requests, remember that we know their read and write set now, we're going to iteratively add the one that increases execution time the least. And we're able to calculate execution time pretty efficiently, because we've restricted the set of things we care about to only be hotkeys. So there's maybe 100 or 200 keys that we have to worry about, and we can do that pretty fast, where we compute the simulated execution time that your schedule would increase to once you run that transaction. To make it efficient, we sample transactions in the queue of requests. So obviously, if you have 100 transactions in your queue, doing this for finding the minimum one or the best one is going to be too expensive. But with a small sample set, maybe 5 or 6 transactions, it's usually actually enough to find a transaction that is good to find that pocket of concurrency. So every time you try to schedule a transaction, you're going to look at a random sample of 5 transactions, see which one causes your execution time to grow the least, and then pick that one. Now, there's a number of tricks that we do to actually perform that execution simulation fast. I won't go into them now. I'll be happy to talk on them afterwards. But the core idea here is that the only thing that you really care about is hotkeys. So you don't have to worry about all the keys. You just worry about the in-flight transactions and the current hotkeys. And that makes it very fast to compute. Or at least, if you're writing to, comparatively to writing to disk, it makes it very fast to compute. So let's look through an example here. You have 3 transactions in the transaction queue here. So the dark blue transaction, the blue one, and the red one. And let's say that we start with transaction T1. Again, the random choice, it did not seem to matter in our experiments. So we execute it first. Takes 2 units to execute. And then we try to figure out which transaction we want to execute next. Now, there's 2 transactions that we could choose from, T2 and T3. So let's try T2. Let's test the schedule T1, T2. Well, T2 conflicts with the write of T1, and so that read needs to see the write, and so would have to wait. It would have to wait for the write to finish, and so it would take you 4 time units to execute the schedule. Instead, if we look at T3, T3 reads X and writes Y, and as a result, can actually start earlier. And so it can start immediately after the read of T1 has finished. And so the total cost of executing that schedule would be 3. So it's a cheaper schedule to execute. And so our algorithm would then pick T3 to run next, and then run T2, leading to 5. Again, that's very basic, and it's basic by design, because concurrency control, to be worth it, has to be implemented cheaply. But even though it's such a simple-looking idea, the final schedule is actually optimal. And we were very surprised to see that in many, many workloads, we actually did find maybe not fully optimal, but close to optimal most of the time. Because of the fact that you just find these pockets of concurrency, and there's enough diversity in the workload, there's enough different transactions that don't conflict with each other, that you can always pick one to run with. You have these friendly groups of transactions that you can always pick from. And that's why it works so well. I'm not going to pretend there's not cases where it doesn't work, but for most workloads we could think of and test, we were able to find pretty close to the optimal workload. And again, it's because most workloads have this diversity of transactions that you can create friendly groups through sampling that form these pockets of concurrency that you can execute. So we're still in the early stages of designing these concurrency control schedulers. But the results that we've seen are actually pretty promising. Now, I'll show some evaluation in a sec. But there's multiple other things we can do here. I've presented you a very basic, greedy algorithm that I'm claiming works well in a lot of cases, but who knows? There might be workloads for which, commercial workloads that we haven't seen, for which it doesn't work. And so we're continuing to investigate how smart we can be with those concurrency schedulers. There's a trade-off between cost, the information that you have, statistics that you need to collect, but we haven't yet fully explored the space of the trade-off, and I think reinforcement learning to figure out how to explore the schedule space iteratively is a very promising one. The other aspect is that as transactions move from those kind of boring templates to agents making calls, then maybe we could tickle the agents to make just the right calls, such that they make calls that are helpful for us and actually design both the concurrency scheduler and the transaction generator work in tandem, which I think is something that we're pretty excited about. So how do we actually go about implementing this? Well, as a reminder, we did not want to touch the correctness of the system. So we implemented this as RocksDB, as a bolt-on extension to RocksDB, such that we did not have to touch anything that could affect the correctness of the system. At worst, we'll give you worse performance, but we'll never give you wrong results. So we implemented the SMS scheduler as a bolt-on layer on top of the RocksDB, both the pessimistic concurrency control of RocksDB and the OCC logic. And then, as normal, RocksDB goes onto storage. Now, we did implement a custom concurrency control. Again, this is a rite of passage. As a database PhD student, you need to build your own concurrency control. Otherwise, you just can't graduate. And so we did have one where we get better results, but I'll focus on the bolt-on approach where we did not touch the correctness of RocksDB. So the results look like this. We tested out on a few database benchmarks that are pretty common, and we looked at the results for scheduling on top of optimistic concurrency control and scheduling on top of pessimistic concurrency control. And in both cases, we're able to achieve up to 3x performance gains just from that scheduling. So the results of TauBench is a benchmark that was released a few years ago and represents the workload of Tau, whereas Opinion TPCC represents sort of traditional OLTP style workloads. And for both Opinions and TauBench, we're able to achieve between 2 to 2x performance improvement. This is without touching the concurrency control itself. This is just through scheduling transactions. If there's no contention, then we suffer from sort of fairly limited overhead, like 2 to 3%, because we only look at hotkeys. So if there's no hotkeys, then our scheduler just doesn't get in the way. So we're pretty excited about this idea of looking at concurrency control in databases through the lens of scheduling again. And we're especially interested in it because we feel that this is the way that we as researchers can sort of start tickling some of the more fundamental aspects of database systems without scaring the practitioners who have to handle the consequences of potential data loss if we introduce a bug. I'll say a couple of slides for what we're looking at next, and then I'll conclude. So I said that data contention caused low throughput and lack of performance isolation. And so far I've talked about the low throughput. But the lack of performance isolation is also a big issue, especially as more applications start modifying and accessing the same data, or as you have multiple clients that can potentially contend on data, maybe through different applications or different divisions in the same company, for example. Performance isolation is fundamentally hard. And you can have a tenant that sends many requests, and that's going to hurt the performance of a client that sends only a few requests. Or, and this is a specific problem in graph databases, a tenant that sends long transactions that can hurt clients that are sending many, many short transactions. And the current solutions that we have are pretty coarse-grained. So specifically, they're centered around request rate limiting, where basically what's going to happen is that you're going to throttle the clients once their limit is reached. And that works pretty well to isolate clients from each other, but it's pretty bad for resource utilization. So in the case of Meta, for example, once the rate limit is reached, then the requests are just placed into a lower priority queue. But that's kind of independent as to whether or not there's spare capacity. And so what you find is that the current solutions that we have for performance isolation for contender workloads tend to lead to fairly low system throughput or system utilization. So the sort of traditional way of handling this is something called fair sharing, and that's very common in cluster scheduling. And fair sharing gets you both performance isolation and high utilization. And it does so by ensuring that every client will always get their fair share, and any excess capacity will get redistributed across clients. There's a huge amount of work on fair sharing for cluster scheduling. But transactions make that harder. And so The resource, when we're talking about transactions, is not necessarily just the physical resource, the buffer cache, the write-ahead log, but it's also just the key. If I'm contending on an object, that object is my resource. That is the object that we want to share. And so resource usage, in the case of a database, is going to be the time during which a transaction has acquired exclusive ownership and is delaying others. Those are the resources that we care about. And what we've been investigating is how we can use this scheduling-first approach that we started with concurrency control to ensure that the client gets its fair share. And at a very intuitive level, in the same way as we could minimize the cost of executing a schedule by picking the transaction that makes the schedule grow the least, we can adopt a very similar strategy to achieve performance isolation by picking the transaction that makes the system the least unfair. And in both cases, this is, we can achieve this without touching the critical ground truth aspects of the system. So this is all I'm going to say about it. I'd love to talk to you more about it afterwards. As a quick summary, we know a lot of information about the workload, and we can use it to make the database life easier. So instead of improving the database, let's just take the database as is and make the database life easier. And we can do that for concurrency control. We believe we can do that for performance isolation. And we're sure there's other aspects in which we can do that, for example, for query optimization or query caching. So as an academic, I talk a lot. I do less coding. And my PhD students are the ones who do code a lot. And so this is work that's been driven by Audrey Chang, who's at Berkeley and at Meta. And she'll be around as well afterwards to answer any questions. So with that, thank you very much.